So we're going to determine, like if you were in the field, how does the inflow performance relationship of an oil well looks like, of a saturated oil well. So first let's do some clarifications on, if you remember the phase envelope that tells you in which phase, if I'm single phase oil, if I'm single phase gas, or if I'm in a mixture, how of a petroleum mixture for different conditions of pressure and temperature. It looks something like that. I have pressure and temperature, and I have one line which is the bubble point line, and then I have another line which is the dew point line. The bubble point line separates the area where I have single phase oil up here with a mixture, and the dew point line separates the area where I have gas and I have a mixture. And this is the critical point. So this is single phase oil, and here I have gas, and here I have a mixture. So we're going to assume, for all the experiments we're going to be doing in this video, is that we're actually operating in this region here. So that means one thing first, that the reservoir pressure is going to be here someplace, okay, PR. And then also that the flowing bottom hole pressure, the pressure I have at the sand phase exactly when the fluid is leaving the formation, is also going to be here. Okay, actually we can assume that that's a fairly isothermal process, so we can say that its temperature is constant. So we can say it will be someplace here. So that will be our approximation for this, for our derivation, for our experiment. Yeah, and it can happen. So for example, we have some cases, if we take stock tank oil, we can see that actually this envelope is very much reduced. I have just something like that. So really, for a big range of pressures, I will be operating actually in single phase flow. It's only when I reduce the pressure very low to values maybe low than atmospheric, I will have a mixture. Okay, so in that case, it's easier to guarantee that you are in the undersaturated region. Okay, this we call the undersaturated region. Undersaturated oil, because if we talked about the saturated region, is the region where I have the mixture. So let's do this in an experiment, like if we were in the field. Yeah, let's first sketch our production system. So we have our tubing hanger. Here we have our reservoir, that is an oil reservoir, and we say it's an undersaturated oil. And we're going to assume it's a vertical well. The ground level, then we have the Christmas tree. And then after that we have a choke and control element that we then go to a separator. And let's say here we have some separator facilities. I'm not going to sketch all of them, but at the end you have a valve, you have a meter, and then you have, at the end, you store all the production in a storage tank of oil. So we say actually the meter that we have here is actually measuring at very close to standard conditions. So that's where our rate is going to be measured, the rate at standard conditions. Let's say here we are at P standard condition and T standard condition. Okay, so what we are going to do with our example, we want actually to see, because remember we are looking into this guy here, how this guy is going to perform. So we're going to say, well, we want to get exactly this behavior, PWF, if I change this pressure, the flowing bottom hole pressure, how will the rate of oil that I measure here at standard conditions is going to look like. And we already speculate that this should look something like this. It's a straight line where we have here reservoir pressure. But in order to do that, we have to be able to take a something to measure. So we are going to change this choke. So we're going to get with that different values of rate, okay, from fully open and starting to close. But then I need something to measure this pressure. So what I'm going to do production logging. I'm going to add a piece of pipe. Then I'm going to send a cable, okay, with some instrument attached to the end. That is going to be a pressure gauge. So in this way, if I do this, I have this wire, I have this line, and then I drop down the instrument and a pressure gauge. In this case, I can actually measure what will be the pressure for all of these changes in rate. And I have, of course, some timing effect. I have to be sure that I'm recording and I took a look at the data at the exact time of this tool, but essentially I can do that. And let's put here a person that is lowering the wire. Yeah. And just as a side note, so for historical references, so this was done, and the first really one technology that was enabling of doing this in the oil and gas industry is this bottom hole gauge, okay? This bottom hole pressure gauge. So some pioneers on this area were, for example, Millikan, that I have his picture here. He was a geologist working in Amerada Petroleum Corporation, and after that had a lot of important positions in the oil and gas industry. But he was, let me just put, is Charles Millikan. Okay, just like a side note that is important of the oil and gas industry, that how did we achieve this bottom hole pressure gauge? So first his company, they developed a gauge, okay, a downhole gauge, and here you see how it looks like, but essentially had to have some expanding element. It's like a coil that expanded with pressure, and then you need to have some mechanism to record the expansion. So if it expanded more, that means you had more pressure. If you construct it was shortened, then that means you have less pressure, and then you have to record that in some sort of a mechanism. So this is really very clever engineering and almost like clock workmanship, but essentially was just to lower the instrument because you had no connection to the surface, so the instrument was standalone, so it measured variations in pressure and registered it in a disc. And I think this disc was even not paper but something made of metal and a needle. Okay, so that's very interesting, and was a key. It's called the Amerada pressure gauge, and that was a key component that allowed to improve the understanding of the formation of the inflow, how the inflow performs. I'm not sure if I can rotate this. Let's see. Rotate. Okay, so really enabled to understand, because otherwise I could just put gauges where I had access to, where it was here, let's say here at the wellhead. But then at the wellhead, actually, when I record that, I get measurements of both the inflow and the tubing. And really, you want to be able to decouple them to see how this one behaves. Okay, because typically in the formation I can be in undersaturated, but usually when I go towards the wellhead, I enter into the mixture. So I'm like, here is flowing of single phase liquid, but then I will have flow of a mixture, and then the results won't be easy to understand. Okay, so also for curiosity, you have this paper published in 1930 by Millikan, just showing some of his applications of this gauge in oil wells. So bottom hole pressures in oil wells. And first talks about the importance of these measurements, and then has some explanation of the technology, the recordings that can be shown, and he has some applications made. I think he has even some measurements during drilling, but here he has some measurements during production. Okay, and first at that point was more or less understood, I think, that the relationship was linear, and some work was done for gas wells that we are going to look at later, but essentially enabled, the technology really enabled to do this analysis. Okay, and I think these are some measurements along the well, just lowering a different depth. Okay, I'm going also to put that this paper you can find in SPE 1 Petro that had all of that information. So if we were going to do that experiment, okay, we have already this in place. We have our well, remember vertical well. We have our assuring here that we only have single phase flow. Okay, that means we're doing our test in this region. And then what we do is that we change the choke. Okay, so if you do that experiment, QO, first let's see what happens in time. So first in time we have our QO and we might start at a very high value. Okay, then we lower and we try another value, and then we lower and we try another value, and so forth. A lot of points. You see here in the paper of by Millikan, he has quite a lot of points, I think like 6. Okay, here they have actually a bunch more, 1 2 3 4 5 6 7 8 9 10 11. Okay, like 11 points. We have only 3. And then if you measure and you try here, you need some synchronization, okay, but you see how it looks like for the flowing bottom hole pressure. Actually here we're going to have a very low until time 1 here, time 2, time 3, time 1. So here you're going to have a very low pressure, and then it's going to increase, and typically we have some sort of a transient. Okay, and then it's going to be, because of this, remember we talked yesterday, we have the infinite acting, so we have some time in between, and then we have again another jump, another increase in pressure. Okay, and when we have these points, actually we have here we have a pair of points. So with this one we have a QO1, okay, and we have here PWF1. We have 2 point pairs, and then we can start and we can plot these point pairs in a chart. Okay, and then we have a QOL1 and PWF1. Then we have QO2, that will be this guy here. And this is assuming we're going from an open choke to, and we are choking gradually. Okay, so sorry, it should be the opposite, right? QO, so this is QO3 actually. QO2 and QO1, for example. Okay, and this is PWF1. This will be 3. Okay, and then you can see that if you can pass a line, a straight line through them, okay, roughly, and then that will be your IPR. So essentially what we can say, and this will be here, will be a reservoir pressure. A reservoir pressure, again, we can measure if we maybe take this to 0. Okay, let me just make that sketch. Okay, we take that to 0. Okay, this will be 0, and then this will take this will increase until it reaches reservoir pressure. Okay, this will be PR. And just please keep in mind, this is a shut-in test. It's called a shut-in test to determine reservoir pressure, but this build-up period might take a long time because actually all the pressure in the formation here at the wellbore vicinity has to be equalized. So this might be something that takes a long time. So they typically try to extrapolate, try to take a shorter duration, and then they try to extrapolate what will be the tendency after some more time to which value it will converge. Okay, so from here we have that this is how it looks like, how it is measured in our experiment, and how it has been measured in the field in the early 1900s. And this we can say that actually it has a relationship such that QO is a constant called J, okay, that we are going to define as J is PR and minus PWF, such that when I have here a zero, okay, I have no flow, that means that these two pressures are the same, that means that PWF is PR, okay, and when this one is very low, you get a very high rate. So this is one of the first and very important equation for undersaturated oil flow, and we will see actually for many configurations. So we have radial well, we're going to see later that also you have horizontal well, you have wells that are not necessarily radial, but they are in some sort of an injection pattern. This equation is going to hold. Okay, so this we call the productivity index, and the productivity index, if you see the units, this part here is in bar, and this part here is in standard cubic meter per day. So the units of J are standard cubic meter per day divided by bar. Okay, if we are working on practical metric SI units using bar and using cubic meter per day, not seconds, because of the magnitude of the rates we normally use in the oil industry. Okay, so we can see this is valid for, and we will see later with depletion. So typically you can say J usually doesn't change with depletion. That means that if you now have at another time, okay, if you have that was an sometime t, okay, that you had that line, this was at time t1, okay, where reservoir pressure was 1. But then if you had another time, actually what will happen is that you simply have a scaling down of the curve, but J doesn't change at time t2 for reservoir pressure 2. Okay, this will be PWF and this will be QO. Okay, same J. Is the same J here and the same J here. And of course, please note here that we are just plotting here the straight part. After some point, if you reach the bubble point, then it doesn't follow anymore a straight line. Okay, if you have here PWF, here you have the QO, and so it will be linear until you reach this bubble point pressure, this PB, okay, which is in our case is going to be, for example, here you're going from reservoir pressure up down to here at constant temperature, and you meet that point. This will be the bubble point pressure. Maybe make a sketch here on the left, on the right. Okay, and you have here reservoir temperature. Someplace here you have reservoir pressure, and then you find out this pressure, which is the PB at that pressure, at that temperature. Okay, so at that point below that is going to behave more like a nonlinear, like we explained before, but this is something we're going to leave for later. One thing also you have to be careful is just like a note before we finish the video, is that the effect of measurement errors and variability. Okay, because typically here we have said, well, it's very clean. Here the behavior of rate is very clean, it's simply a straight line, and here we also have said that the pressure is very clean, but essentially we have a lot of variability. In reality, we have a lot of variability in these rates, in the measure rates. Okay, so if you see, probably it will be some fluctuation, and then you have also some fluctuation, you have also some fluctuation, and it will be the same for PWF. Okay, so in that case you have some band. Okay, it's not that you can say it's just one value. Okay, but you have a band. You have to change it here. But you have a band around the number. Okay. Also, something that might happen is that the pressure gauge has some error, associated error. So the pressure will be a value plus an error. Okay, that actually instrumentation currently has is becoming with very high accuracy, but due to time can have some other types of error. Okay, value times the error. But essentially that tells you that when you have your points and you want to you have your PWF and you have your QO and you have your points. Okay, you have to take into account that there is some error associated to these measurements. One is due to this variability, and then the other is due to the error of the instrument. So actually you have some range. This value is not an absolute number, but it can have some variation. And if you see here, we can actually will obtain two very different results if we try to pass a line. Let's see how it looks like through here, or if we try to pass a line through here. Okay, this one will have some J and this one will have another J2 and J1. And you kind of wonder that, you know, which one is the correct one because of the error in measurement. Okay? And actually we have, you see one advantage also is that we need just 1 point. Okay, so if 1 point is available, and reservoir pressure is known, okay, then we have, let's say that we have measured this point PWF1, QO1. Okay, so we come here and substitute QO1 in this equation, JPR minus PWF1. Okay, and we simply say that J is going to be equal to QO1 divided by PR minus PWF1. Okay, which we have all of these, and then from there we can readily calculate the productivity index. Okay, but just be careful with this issue here. So because the value is not simply one value, but you have a range of values that can be due to variability and error measurement in rate and also in pressure. So it might be that the solution you get could be slightly different.